So the topic today is LCD and OLED displays. And we're going to start off with LCD, liquid crystal displays. They're the most common. We all own probably several devices that have LCD displays in them. Most of us have gotten a flat panel television. Those are almost exclusively now LCD, although there's still a couple of manufacturers still making plasma displays, which is a whole other can of worms, which I can get into, but we'll kind of stay focused on the mainstream displays. OLED is a light-emitting diode, and the O stands for organic, and they're the next generation display. You probably have one of these if you own a smartphone, or like a Garmin, or something like that. They're becoming very popular in these type of devices, and you're going to start seeing them also in bigger displays as well. But anyway, starting off with LCD, the thing that I want to get across is that a liquid crystal display is nothing more than a light valve. Each pixel element in an LCD is simply adjusting the amount of light that is allowed to pass through it. And it does it actually in a very simple manner. Now what we have here is a display showing a light source at the back. So these black arrows, that's light. And it's unpolarized light in the sense that just like sunlight, the photons are coming from every which way direction. Now, if it was a sunny day out, and you were driving over here, you'd put on your sunglasses, right? And probably most of us own polarized sunglasses. Now, the next sunny day, take your sunglasses off and just kind of go like this with them, and notice how the amount of light that passes through the lens changes. And that's courtesy of this polarization effect. Now what we're showing here is a filter that only passes vertically polarized light. This guy over here is a horizontal polarizer, and if we vertically polarize the light, theoretically this guy right here will block all the light. Everybody comfortable with that idea? As there's no LCD involved yet. Two passive optical devices and a light source. That's all we're showing here. Now let's add a light source and an LCD. The LCD material is represented right here. And the LCD material with no charge, electrical charge applied to it, will cause the light to rotate 90 degrees. So we have incoming light going through a vertical polarizer, and then it passes through the LCD material, which is sandwiched in between the two polarizers, and this shifts by 90 degrees and allows the light to pass through the horizontal polarizer. Well, that's kind of neat, right? Now, is there light lost in this process? Yeah, of course there is. But the point being is that without the LCD material in here, most of the light would have been completely blocked. So how do we vary then the amount of light that gets passed? Well, we do that by simply applying a charge. and we can apply an electrical potential which will be in direct proportion to the amount of light that we want to allow to pass. So we can go from near black to maximum brightness. Now, one of the complaints with LCD displays is that you can't get a really black on the screen. There's always some residual light. And this affects what they call the dynamic range of the video, the contrast levels, and so forth. If you've ever gone shopping for a computer monitor and you look at the contrast ratios, some of them are like 1,000 to 1 and some of them are 1,000,000 to 1. Don't ever go by that number. That's like the number of watts coming out of an amplifier. How is it measured is the question, and there's a lot of different ways to measure it. But bottom line is an LCD cannot extinguish all the light. So you can never have something that is completely black on the screen. You can have close to it, but not completely. So anyway, the principle of operation here is that by varying the charge on our LCD, we can vary the amount of light that's passed. Now, this means then that every LCD display has got to have some sort of a light source, right? And the light source could be a fluorescent lamp, it could be an LED, or it could be a passive type device where you actually use exterior ambient light, and you channel that to the back end of the display. That's not popular at all today, but it was used years back. Well, how do we get color? We get color by simply putting filters in front of the various elements. And here we're showing a twisted, or a thin film type display where each one of these squares represents a pixel. And the thing that's interesting is your backlight source is got to be some kind of a white light in this case. And this light gets passed through our LCD material and the polarizing filters, and then gets tinted red, green, or blue according to the filter that's applied. And so, for example, I'll be passing around in a minute a sample LCD panel, and these filters run from top to bottom. So there'll be a red stripe all the way from the top to the bottom, a blue stripe, a green stripe, and they just keep repeating like that. The LCD material itself can pass light from infrared up through the lower end of UV. So as far as visible light, which is what we're interested in, it passes that with no trouble, and there's no significant attenuation of any of the light frequencies within our visible range. Now,
the amount of rotation of polarization the same for the different wavelengths, for the different colors?
Yeah, it's basically how much do you want to pass. Now, what's interesting is that to obtain white, you don't pass equal amounts of red, green, and blue, those primary colors. What you do pass is approximately 59% red, 30% green, and 11% blue. And that, those ratios are chosen to correspond to the way our eyes cones in our eyes. I always get the cones and the rods mixed
We
up.
don't know, you can say it.
Yeah, but anyway, it has to do with the way the human eye responds to what's white. And I'll show you a chart in a few minutes called the chromaticity diagram that shows how the colors are laid out with respect to wavelength. And then white is in the center. But, so to your question, which is very good, in this case, if we wanted to make this panel white, we would make the red 59% of the light, the green 30% of the light, and the blue would be 11%. And for some forms of high definition, that ratio is slightly altered, but not by more than about a percent or two. So it's very close.
So would they do that by having red, green, and blue different width stripes, or is it just?
They're the same width. Yeah, so these pixel elements are all the same. And so it's like if you've been looking for a camera, a CCD camera, one of the things that you look for is what is the actual size of the pixel element. Now, of course, CCD device, charge couple devices, completely different than what we're talking about. But they're similar in the sense that they're made up of a matrix of equally sized devices. And these devices are going to be addressed. So we have address and data. So we're actually going to be addressing each one of these elements. And we'll address them with the amount of bias necessary to produce the color that we're looking for.
I think you said this before, but a pixel is 9 of those little squares on there, right?
A pixel would be one of these,
Just
one
one
of
of
these
those?
squares. So for monochrome, and remember the LCD device is colorblind.
Oh, all right.
So each one of these squares represents an LCD pixel. But if we want color out of it, then we have to put the filters in front. So these are all equal size pixel elements. And for a color pixel then, you need 3, red, green, blue. That makes up one color pixel element, but each one of these by themselves represents a pixel. Now, to put this in perspective, if you have a nice 1080p display at your home, a nice flat panel display, that has over 6 million of these pixel elements. That's a bunch, right? So to control this, what is basically a matrix, we have address lines, and it's just like memory. It's just like addressing memory. And instead of addressing each, if you were to consider this like a RAM bit, instead of just putting a 1 or a 0 here, we have the ability to vary the bias, and that comes in at this point. So, and that's all part of the drive circuitry, which I'll get into in just a minute. So here we're showing the typical construction of an LCD display. You have some sort of light source. In this case, they're showing fluorescent backlights. The fluorescent backlights are still being manufactured, although the they're being quickly replaced by white LEDs. For one thing, the white LEDs require much less voltage and current to perform, and they also last better. But the flip side to it is the fluorescent lamps are an old technology, and it's very cheap to manufacture. So it's actually cheaper to use fluorescent than it is the LED backlighting. But in either event, it's a light source.
Those are the same LEDs that are in the flashlights? The white-
Same idea, yeah, same idea, yeah. In fact, so what at this point, I'm gonna pass around, this is a fluorescent lamp that came out of a computer monitor. And you can see it's just, there's two of them in here, and it's just pencil thin. And there generally would be, for this size, there'd probably be about 6 of these units in the back end. Now, they're showing here a diffuser, and this is to prevent bright areas. You know, you have to even this light out, right? Otherwise, you're going to have, you know, bright stripes in the screen, and you think, well, that couldn't be very much. The diffuser is what makes up the bulk of the whole business here. So I'll pass that around. That's the diffusion plate that came out of this thing.
Steve, you gonna be able to put your computer screen back together?
And then what we have here, are the polarizing filters, the vertical and horizontal polarizing filters, and these are just sheets of plastic. The actual display is nothing. It's just a very thin sheet of glass, and when this gets passed around, be a little careful because the edges are kind of on the sharp side. But what I'd like you to notice is that the board here is attached with flexible ribbon, and it's what they call tab bonded. Now this means that these flexible ribbons with all of the connectors are not actually soldered on. They're pressed on, and in between the copper foil connection of the flexible cable and the copper connection, which is etched onto the glass, they use little tiny microscopic solder balls, and they actually squeeze these two together and smush the solder balls down, and along with a little adhesive added in, that is how these babies are attached. You'll also notice that there appears to be like an integrated circuit in the middle of these connectors, and it is. It's an integrated circuit. It's a driver. And so what we're doing here is these connections are your address and your data lines. And the main microprocessor that's controlling all of this is this little square IC. And the whole business then gets hooked up to your video processing circuitry. So that's essentially what we're looking at. This part here with the colored stripe filters, that's part of the glass panel that's going around now, and that's your business. You know, that's the whole working end of it. The rest of it is all optics. These sheets are all optics. Now, another type of LCD, which is very popular. Any of you have a projection TV?
Right here.
And we've got one right here. Now, there's a couple of different, there's two main types. This happens to be something called a DLP projector. And what I'm going to describe here actually uses 3 LCDs. So if you had a Sony projector, and those are the ones that I'm most familiar with, you'd have a lamp, and this lamp would produce a very bright light. We take that light, we culminate it, and they call these dichroic mirrors, but you're going to see in a minute that they're nothing more than prisms. And these prisms take this white light and they split it. So this first one splits off the red, and we feed it to an LCD panel that controls the amount of red content that we want to project onto the screen. This one splits off the blue, or the green rather, and this one splits off the blue. Now the reason that we go red, green, blue is because red is the lowest frequency, green is the next highest frequency, and blue is the highest frequency. So optically, that's the order in which they have to be split off. Now, if any of you have like a little prism that you set, on the table and let the sunlight through, if you notice how the colors spread out, you'll notice red is at one end, green is kind of in the middle, and the blues and purples there at the other side. Here's an actual picture of this device. The light is coming in right here. There's a cover here, and that's why you don't see any light. But you can see that this is white light here, and this is your first dichroic mirror, which is actually a glass prism. And notice how it takes this red and funnels it over to this LCD shutter. And same way, here's your green, and once you pick off the green, then all you have left is the bluish light.
Can you go back a slide for a minute? Yeah, that one. So that where the LCD panel and the polarizers, is each one of those in and of itself similar to what you just passed around as a whole?
Correct, but with no color filter.
No color filter?
No color filter, because we're splitting the colors here.
Okay.
So this is a light valve for the blue, a light valve for the green, a light valve for the red, and this device right here is another dichroic assembly which combines the 3 colors and sends it out to another culminator and focuser and up to there's a mirror
But
in the
these are all
screen.
miniature little things, they're not.
Right. Yeah, they're small. They're really small. Now, well, I'll kind of leave that there because projection TV is dead. And it's all being replaced by big screen, except for this type of application. And these devices are almost exclusively DLP. With the exception, Sony makes some of the better style.
Steve, I'm sorry, but it's not DLP, what's the other one?
Sony never gave another, it was a 3 LCD.
Oh, okay.
3 LCD versus 1. So the DLP uses 1 and the Sony's use 3. And if you go to movie theater that's using like 4000K type projectors, they'll be using something that's very similar to this as well. So what about if you have a problem with LCD? Well, they fall into a couple of different categories. One is very uncommon, and that's distorted video. If you have distorted video, I'll almost guarantee you it is not your display. If you have distorted video where, it just doesn't look right, you're not getting enough fine detail in the picture, that's a problem with your video process circuitry. That's a whole other discussion, so we won't get into that. But there are very common problems. This is probably one of the most common, where you have either vertical or horizontal lines. Now, you know what causes this? What causes this are those flex connectors and the tab bonding to the actual LCD glass. And you can actually fix these yourself, because all that's happened is that the connection has come loose, and sometimes all you have to do is rub the flexible cable with like an eraser, and you can get that to mate again and solve your problem. But this kind of a problem is 99% of the time is generated by a bad connection on the flexible connector, and 1% of the time by a bad driver.
If you got a display with 6 million pixels, how do you ever get all of them to work at once?
Well, that's an excellent question. And let me put that on hold for just a second, because I'm going to address that. Well, let's do it now. We'll come back to this. Where did it go? Maybe it's not in this one. But I use this as an illustration. They're showing the problem of the dust particle. If you have when you are rebuilding these assemblies, it has to be done in a clean room, because if you get any dust in between, it's a problem. But the other thing is, I've got, for example, I bought one of these Asus monitors, dirt cheap, 27-inch 1080p for my computer, and I love it. But right about there, it's got a pixel, a red pixel that is stuck on. And so when it comes on initially, and the screen is black, I see this red dot. Now, since there's over 6 million of these puppies, once the screen is no longer black, I can't find it, right? But if you have over 6 million pixels in a regular HD display, will you have defective pixels? And the answer is, yeah, you betcha. Now, the thing of it is if the pixel is stuck on, or there is a group of stuck on pixels, you will probably notice it at some point or another. However, if you have dead pixels, which are not passing light, you'll never be able to find that unless you actually take a microscope and examine, the display quadrant by quadrant, which is done at the factory to ensure quality control. But yeah, so 6 million pixels, and you have 1/100th of them are bad. You still have a big handful of pixels, but most of them are dead. Now, probably the best way to relate this is again to RAM. So, we have, by 4 gigabyte sticks now of RAM. Are there any dead registers? And the answer is yes. But when they tested those, they mapped them out, and so your computer doesn't use them.
That oftentimes is done in power up too.
Yeah, I can.
Will scan all the memory and down anything that's bad.
Yes, yeah, correct. And, there's one other, I had a senior moment there. It might come back to me. But yeah, there's defective pixels. And, that was one of when I was working, that was like the one customer complaint that I hated to have to deal with, you know. Well, I just spent, $6,000 on this and I got 2 red dots or I got a green dot. Well, too bad.
So congratulations.
Let's take a magic marker and block them out.
Just to show you one of the problems with the projection sets. Now, we all realize this got a lamp in it that's running real hot, right?
Yeah.
Eventually, it takes these are the polarizers. Remember, you have 2 of them. You got a vertical and a horizontal. Eventually, it cooks these until, there's nothing left of them. And as they start to cook, they start to distort the image. And so you can get all sorts of funny displays. If you've got a projection TV and it's starting to give you blotches of color, well, you've got a bad polarizer. So, and that's the nature of the beast. So, pixel failure, it's either going to be continuously on or it's going to be dead. They don't. They don't, because you would think that, because anything that allows you to make that much light, which is what you need, is going to create heat.
Oh, okay.
And the thing of it is, what's kind of interesting is if you, where are we going with this? If you take and put a thermal probe here,
Yeah.
in the lamp compartment, and put a thermal probe here and here, the hottest parts are at the LCDs. Because the light is concentrated,
Oh, okay.
so.
I've got a question to ask you. What happens if you guys, if you make those, they could do our returns too also or not?
I'm sorry?
If you do an interference with that, and that could do the interference too also or not? And that's what I'm asking you. That's the question.
You mean for this here?
Yeah, if the whole thing went down, and that could do the interference if you have videos or something like that, or what?
Well, if the first thing when you have a problem here with no output is to check to see if your lamp is working.
Okay.
And if the lamp is the weak link and is the one that fails the most. And the second thing that fails is the power supply. In this case, this is a power supply like you could find in Les's laptop supply, but in this case, the output transformer is wound to give us about a kilovolt and a half out of here, which is necessary to fire a mercury vapor lamp.
Mm.
So this is also a high failure item.
So I do have an old Sony rear projection high definition TV.
You're in trouble.
Well, the first thing they warned me about was the lamp's gonna go. When that lamp goes, does it just go suddenly or does it diminish over time?
It diminishes over time, and there's actually feedback circuitry that measures the amount of current being drawn by the lamp. As the lamp electrodes age, remember this is a mercury vapor lamp, so it's like an arc welder in there.
Okay.
As the electrodes age, the amount of current required goes up. And when the current gets to a certain point, is supposed to shut the power supply off, and then you have a dead set. And in the case of the Sonys, you'll get the LED on the front will blink in a certain pattern. And
But as long as it seems bright enough to me, there's no problem.
right, but if the lamp is a couple, 2-3 years old, and you were to change it with a new lamp, you would be really surprised at how much brighter your picture got. And by the way, that's also very true with fluorescent lamps. Fluorescent lamps diminish in brightness over time, and so do LEDs.
Really?
So that's kind of a interesting phenomenon. Well, let's take a look at this here. I wanted to try to get a flavor of the different OLED technologies out there, because it's very cool. The thing about OLED is it is a light emitting device in of itself. It requires no backlight. These are light emitting diodes in the form of white diodes or in the form of red, green, and blue diodes. And they can be formulated, manufactured in a number of different ways. And the beauty of them is this. With a regular LCD display, whether it be your computer, laptop, or whatever, as soon as you move off to the side, can you see it clearly? No. But with OLED, and that's because of the polarizing filters, the optics involved. But with OLED, you can look at it from any angle and you can see it perfectly well. We can also achieve with OLED better color fidelity, and I believe there's a chromaticity diagram on here that we can look at. And we can also get 100% black, because if we want black, what do? Shut it off, yeah. So the contrast ratio you can Mickey Mouse around with LCD, and you can say, oh, it's 50,000 to 1 or whatever, depending upon how you're lying about your measurement. But with OLED, you can get 1,000,000 to 1, and it's a real measurement. So let's take a look at how this works. Essentially, you have a light emitting diode that's built just a little bit differently. You've got an anode down here that a positive charge is applied to. You've got a cathode that a negative charge is applied to. And then you've got what they call an emissive polymer layer and a conducting polymer layer. Now, these form a sandwich. And essentially, what you need to appreciate is that although in this particular illustration, they're showing a glass cover for, that this is all built on, the light is going to come out the bottom through the anode. You all with me on this? Now we'll get to how it makes a color, a specific color in a minute. Now, what's kind of cool is this. Let's consider 1 pixel. So we're going to apply a negative charge to the cathode, positive charge to the anode. And this sets up a bias region between these 2 points right here. Now there's a couple fancy terms that I can't remember, although I've got them written down if anybody's interested. Anyway, bottom line is you get electrons coming this way and holes coming up this way, and they start to recombine in this area. And they recombine according to Coulomb's law, and it creates an electrostatic field. And this electrostatic field will generate photons. Now, the color of the photon emitted, or the frequency of the photon emitted, is going to be determined by this chemical composition here. So for red, we have one chemical composition, for blue another, for green another. So essentially, that's it. It's very straightforward, kind of the theory of it. But the actual manufacturing of it is another story. And the principal problem with organic LED right now is how long the LEDs are going to last. And the blue LED is got the shortest life. So that's the problem child. Kind of like Blu-ray discs were held up for years while they tried to get a blue laser diode that would last for more than 20 minutes. It's the same concept. So anyway, this is showing us with the charge, and then this is the two fancy terms I was looking for, LUMO and HOMO, and anybody wants to know that, I'll tell you later. I have to look it up.
No, I'm just exercising.
Oh, exercise, okay. So, anyway, so bottom line is you can see what's happening here is this is where the holes in the electrons combine. They generate this static charge which emits photons or light. And this is showing us the amount of output versus the voltage. And you can see that the output corresponds to a point to the amount of bias applied, which is the same concept as you have in a standard LED. This is showing us some of the different chemical compositions. This is actually a pretty good slide here. And then this is giving us a little more about how the polymers are chemically put together. And I won't get into that. I'm not going to walk anybody through that because I don't get it. But the bottom line is that what we've got here are the ability based on the chemical composition chosen to emit blue, green, and red light. And notice that there is some overlapping, which is standard. And the same rules apply. If we want to make white, then we have to give approximately 59% red, 30% green, 11% blue. Now this is what's kind of cool. This is called a chromaticity diagram, and this was developed back in the 1930s. And it's sort of the standard that's used by people that are involved with anything in the video industry, whether it be displays or cameras or anything having to do with optics. Anyway, the point being is that white is sort of in the middle, and then if you look at how the diagram is set up, you can see how as you shift in frequency, you'll go into the red zones. And you can create any color imaginable by applying the right amount of red, green, and blue, your primary colors. Now, here it's showing us that there are different ways of actually making these displays. So they have something called spin coating, and I'm not really too much familiar with this, but I have seen the inkjet printing and the screen printing. They've actually made what are basically inkjet printers to manufacture a display on a piece of plastic like an overhead transparency. Very cool. But in any case, it has to be built up in layers. You have to put it down layer by layer. Here's an inkjet doing this. Here, it's flexible. Can produce them in rolls, which is very cool.
Is that considered a mature technology, Steve, or?
No,
No?
not yet, no, it's still very much under development. And, but, for example, right here, you see how, you can see some clip leads?
Oh, yeah.
And you see that this is a piece of flexible
Yep.
material, it's like a piece of overhead film that you might use. They can actually do this on like a fabric-y type of stuff. It's really cool. And I think I'm gonna pass over this. It's kind of on the boring side, but basically they're showing here, all right, here's a multi-layer structure made in a vacuum environment, and here's a bilateral structure made from a solution, which requires no vacuum. And here they're showing some shadow masking in a vacuum for creating the red, green, and blue. Let's see it. There's a couple of interesting pictures here. Yeah. This is kind of neat. Here they're showing what would be, this is a true RGB OLED display. Very power efficient, low production costs. Here they're using white LEDs to produce white light and then putting filters in front of it. And this is very similar to LCD. And also when you're just dealing with one type of LED, it's much cheaper to manufacture. And frankly, I don't understand this one too well. I don't know where the application is on that one. And finally, here's our chromaticity diagram again. Now, the thing that I'd like to draw to your attention is that this triangle that they're showing, this one here is the amount, everything that is within the triangle is what this particular display, which is a thin film LCD type screen, can display. This is all the colors it can display. Whereas here, notice that this can actually display a larger amount of color. And the color that we're interested in is in this range over here. This is where we judge most color fidelity, is with reds, because reds make up like face tones and things like this. The blues, not so much. Green, of course, is important, but the reds, it gives you a much, much better red rendition. And again, we have a matrix. We're addressing it in matrix form. We can have active or passive. And they're just kind of showing us all the different devices that you find these in. So probably several of you have got OLED displays in your smartphones.
Well, we're gonna lose the blue real soon?
No, because the beauty of this is the OLED is very well suited for displays that are only on for short periods of time. Where they are not so well suited yet is for like a big screen TV, where it's left on for 10 hours a day. That's where, yeah, that's where you're gonna have problems with longevity. But they're getting that resolved. And this one here, this is one that I was involved with before I retired, and this was just a 13-inch display, but the picture was absolutely unbelievable. I mean, nothing in the LCD or even the picture tube type sets could come close to it. So when these start to replace the traditional LCD that is available now, you're going to be really surprised by how beautiful these pictures are.
When's that gonna happen?
Pardon?
When is that gonna become available?
Well, the trade rags say that Samsung and LG are gonna have some larger screen devices out at this winter's CES. So I don't know, I haven't seen anything over 27 inches yet myself.
You probably have one at your house already, right?
No,
Oh.
these were very expensive. But anyway, that's the concept of organic LED. It's exciting technology. It's already here. It will displace what's currently being manufactured and sold somewhere down the line.
Can we tell by looking if we got one? It's kind of a crummy thing, so it's probably not mine.
No. No, this is not, because as you change the, if this was OLED as you did this, the brightness would not change.
Okay, thank you.
So that's probably the easiest way to tell. Well, guys, that's all I got for you.
Excellent.
Thank you.
Thanks, Steve.